We're going to run through a couple of examples of problems involving the radius of convergence and specifically applying the ratio test in those cases. So the idea here is, and we saw this when we worked with geometric series expansions of rational functions, and honestly that's what most of these are going to be. If you think about a geometric series only converge when your R value is between -1 and +1. And so when we create these other series, it's possible that they may be convergent for any value of x that you want to substitute into it. But it's also possible that for certain values of x that you put in, you get total garbage and it adds up to infinity. And for other values of x, the series is actually going to approach the value that your original function was supposed to give you. That's the idea. So most of these don't work for every single value. And that's where the idea of radius of convergence comes in. Most of these series are centered around some value. The one that we saw that I graphed on Desmos was centered around 0. A lot of these geometric series are, and you can go up about 1, you can go back about 1, and it's pretty accurate, and everywhere outside that range it's not. The radius of convergence is the amount that you can go up or back from whatever the center of your expansion is. And again, most of the time the center is going to be 0, but there's some special cases. Anyway, let's go ahead and take a look at this. So the key here, you're not going to apply the ratio test to the original function. And I think that's the mistake that people tend to make on these problems, okay? You have to get the series first. So if you follow the directions, I think the directions will ask you to list a few terms of the series and get the general term of the series and so on and so forth. So anyway, we need to get this in the form 1 over 1 minus a value. Okay, so we can factor out 5, and that's going to be 5 times 1 over, and again, it needs to be 1 over 1 minus the input. So instead of a plus x, I'm going to do 1 over 1 minus x. Okay, well, this setup, 1 over 1 minus x, is the geometric series 1 plus x squared, and so on. Okay, this is going to be that same series, except our terms are 1 plus the input of -x plus the input of -x squared, and so on. And so this is going to be 1 minus x plus x squared minus x cubed, and so on. It's an alternating series, okay? So we need to put this together. We need to find the general term. The general term here should be alternating signs of -1, so -1 to the n, and then just x to the n, okay? And that should alternate the way we need to see it. Now, this series was also multiplied by 5. Okay, so this whole thing gets multiplied by 5 here, and it's 5 minus 5x plus 5x squared, and so on. So the final series, it's alternating, so you've got -1 to the n. You did multiply by 5, but each term just has a 5 in front of it, and then we have an x to the n. Okay, so that's your general term. And if you're going to do this with summation notation, you would write it in this form. Okay, so where does the ratio test come into play? So you're going to take your sigma setup, n equals 1 to infinity. We have -1 to the n times 5x to the n, okay? What the ratio test says is that this series is only going to converge if I go out infinitely far, if the farthest term out divided by the term that comes before it, if that ratio is consistently going to be less than 0, consistently less than 1 as I go out to infinity, then basically it's going to behave like a geometric series as we go farther out, and it's going to converge, okay? If that ratio is not less than 1, then it's going to be a divergent series. If it's equal to 1, it's actually unclear, and that's something we're not going to deal with in this course. But anyway, if it's greater than 1, it's going to diverge, okay? There is an absolute value here. The absolute value, remember that that R multiplier has to be between -1 and +1. So a lot of times they'll use this, and this just means that the ratio has to be between -1 and +1. Anyway, let's put all this together. So you're going to take the general term from your series representation, not the original function, okay? And that's what you're going to substitute in. So we're going to take the limit as n approaches infinity. So we're going to go infinitely far. we're going to take the n plus 1 term, okay? Now be careful, there's now going to be an x variable, and this is just a function with different values. N is representing different terms, so make sure you're substituting in for n. We want the n plus 1 term, so it's negative 1 to the n plus 1. 5 doesn't have anything having to do with an n. And then we want x to the n plus 1, okay? We want that divided by, so that's the n plus first term, divided by the nth term. So that's negative 1 to the n, that's 5, and x to the n is our term. Now, a couple of things here. Technically, there's an absolute value, okay? So we technically put the absolute value around this whole thing. The negative ones in this don't really matter. And in fact, if you want to throw them out, it's going to work out okay. Notice here, n of these will cancel n of these. That leaves us with a single negative 1. However, all of these other values here are going to be positive, and the absolute value is going to knock out the sign on that negative 1. So honestly, if you just want to go ahead and pull out the negative 1 altogether, that really will make things a little bit easier here. Okay, we just need to simplify this now. And notice, I can divide a 5 out of the top and the bottom. Those are gone. I can divide n x's out of the top and the bottom. And that's going to leave me just with, the limit as n approaches infinity, of just a single x. Okay, notice, there's no n. Okay, n of these x's canceled n of those x's. The n's are gone. Okay, this limit is doing nothing because there are no n's left. Okay, but this ratio has to be less than 1. Okay, so as n goes to infinity, doesn't affect x at all, that's my limit. Okay, x just has to be, the absolute value of x just has to be less than 1. Okay, a lot of times you want to take that absolute value out. Okay, if you take an absolute value out, x could have been positive or it could have been negative. So we would say that x has to be between negative 1 and positive 1. Now, this is what's referred to as the interval of convergence. Okay, I don't think I asked you for this in these problems. That's the interval of convergence. Okay, if you notice, 0 is exactly halfway between negative 1 and 1. This is centered around 0. Okay, so basically, if you graphed this, if you wrote out a lot of terms of this series, it would look real close to the function 5 over 1 plus x for values between negative 1 and 1. Okay, it's a good estimate for this function for anything between negative 1 and 1. If you put anything outside of that range, negative 1 and 1 in, this doesn't have anything to do with the series. Okay, that's really the key. The radius of convergence is just how far you go up from the center. I can go up 1 from 0. I can go back 1 from 0. Okay, so you're saying there's this range of values forward and backwards. That's the radius, how far you can go up from the center and how far you can go back from the center. So the radius of convergence, which is actually the only thing I'm asking you for in these problems, the radius of convergence is just 1 for this. Okay, so it's a pretty tight range of values for which this will converge. All right. If you think you can do that now, you can go ahead and work on the rest of these problems. I will do a couple of other examples if you feel like you need to see them.